All right, well, this is a video for the first day, or really the preview to the first day of Unit 15, Day 0. This is a basic review of statistics you should have learned in Algebra 1. It's been a couple of years, and we're going to kind of just talk about some of these things that you did back then throughout this unit. So I just wanted to make sure that we are all on the same page and we all knew the background information going in before we do the new stuff. So none of this should be totally new today, hopefully. So hopefully you have this worksheet. If you don't, you can download it off my website and follow along that way. But first thing I want to talk about is different distributions of data. So I'm just going to read it along here. Distributions are described by the shape, symmetric or skewed, the center, and the spread or variability in the distribution. A distribution that is approximately symmetric can take different forms. So these are both called bar graphs or histograms, and they show how frequently the different data values are represented. Both of these data are approximately symmetric because if you draw a line down the middle, they're fairly symmetric. This one, not exactly, but pretty close. Because a distribution is described as mound-shaped if it is approximately symmetric and has a single peak, like the example in the left. So it's mound-shaped because I can kind of draw this type of curve around it. So another word for mound shape is called bell-shaped, called a bell curve. We're going to be talking a lot about that in the first couple days here. This one we wouldn't call bell-shaped over here because it doesn't have that same sort of peak in the center here. Next way we can describe a distribution is as skewed to the right or skewed to the left if one of the tails is longer than the other. So like this over here is called skewed to the right. Most of the data is over here on the left. So most of what we're dealing with, where that bell is over here, but then I've got this extra long tail on the right. And on the other side of that, this is called skewed to the left. Most of the data is over here on the right. There's a little bit of info on the left that kind of skews it out. These are called outliers. Some extremely high or low data values that are kind of pulling everything, in this case, pulling it to the right, pulling it to the left. It says the mean of a distribution is interpreted as a typical value and is the average of the data values that make up the distribution. It's often represented by the symbol X bar. So I'm going to be using that a lot this year also. X bar means average, so mean, think of the word average, when you add them all up and divide by however many data elements there are. And the other big value we're going to be looking a lot at is called the standard deviation. That's a value that describes the typical distance from the mean, on average, how far data is away from the mean. And that's represented by this symbol. That's a Greek lowercase letter sigma there. But whenever you see sigma, you want to think standard deviation. Okay. So let's flip to the next page. And we got an example. It says, consider the following histograms. Histogram 1, 2, 3, and 4. And the descriptions of the 4 histograms given below them. Match the description of the distribution with the appropriate histogram. Okay, so here's the different histograms. And then here's the descriptions. We've got, says distribution A is skewed to the right with a mean of 100 and a standard deviation of 10. B is approximately symmetric, or mound-shaped, or bell curve, mean of 100, standard deviation of 10 also. C is still approximately symmetric with a bell curve, mean of 100, standard deviation of 40 now. And D is skewed to the right. Okay, so we can at least look at these and say which ones look approximately symmetric, which ones look skewed. And hopefully you see that that one's fairly symmetric, maybe a little bit more data on the left, but fairly symmetric. This one I'd say even is more symmetric. These two are skewed to the right because most of the data is over here on the left. There's a little bit, it's kind of pulling it to the right. So this one's very skewed. This one, maybe not quite so much, but there's still this extra tail on the right that makes it skewed to the right. Okay, so these two are definitely skewed right. Again, they're called skewed right because where the extra data is. These are bell curves. or mound shaped. So now we got to look at the mean and standard deviation. They're saying all the means, all the averages are 100. So that's not really going to help us. But if you look at the standard deviations, we've got standard deviations of 10 with these top two and 40 with these second two. What standard deviation tells us, remember, is how spread out. So these 40s, standard deviation is larger. That means these data values should be more spread out. So that means we have to go back up to the top and look at just how spread out these data values are. Okay, so let's start with the symmetric ones here. Take a look at the range. We go from, I'd say that's 70 to about 125, as opposed to this one down here, which is going from 0 to 200. So which of those two is more spread out? Well, clearly 0 to 200 is a lot bigger range than 70 to 125. So this would have the larger standard deviation. This must have the standard deviation of 40, and this must have the standard deviation of 10. So histogram 1 is approximately symmetric with a standard deviation of 10. So approximately symmetric, standard deviation of 10, it looks like distribution B. Let's jump down to 3. That's the other bell-shaped one with a standard deviation of 40. So histogram 3, approximately symmetric, standard deviation of 40, so we're going to call this one C. Okay, then take a look at this one. So this is, looks like it goes from about, what's that, 85 over to 145. The data is pretty representative throughout there. This one goes from 50 over to 350. So this one definitely has a larger spread. These data values up here are really skewed out. And even if you look at where most of the data is, this goes from 50 to 175, and even if we ignore these outliers, the spread is still bigger down here than 85 to 145. So scales really matter. You got to pay attention to those. So I would say this would have a larger standard deviation. This would have the smaller standard deviation. So that means histogram 2 is the skewed right with a standard deviation of 10. So that would be A. And that leaves D for 4, skewed to the right, standard deviation of 40. Okay, so that's what standard deviation really tells us, how spread out the data is. All right, going on to the next page. Example 2. Histogram below shows the distribution of the greatest drop in feet for 55 major roller coasters in the U.S. Part A says, would you describe this distribution of roller coaster maximum drops as approximately symmetric or is skewed? Explain your answer. Okay, well, what do you think? I'm zeroing in on those two values. If those two weren't there, we could maybe make a case for approximately symmetric, but most of the data is over here on the left. We've got some outliers, so I would say it's a little skewed to the right again. So I'm just writing skewed right. And the reason I would say it's skewed right is that there are some extreme right values that are affecting the data. So there's nearly not a lot of big clump. There is a big clump, but there's more than just a big clump. So that's why I'm saying it's skewed to the right. Okay, B. Is the mean of the maximum drops distribution closer to 90, 135, or 240? And explain your answer there too. Well, take a look at 240. 240 would be right about here. And it wouldn't really make sense for the average to be out that high. I mean, these are skewing the mean. They're pulling it to the right a little bit. But a lot of data is down here. So the average is going to be concentrated more in the middle of this section, I would say. So this one's too big. So now we're down to 90 and 135. So 90 is right about here. 135 would be closer to here. You could probably make a case for either. Most of the data is around 90, but I would probably go with 135 because there's still a good amount of data to the right of that, especially these extreme right values that are going to pull the mean a little bit. So I'm going to go with 135. And remember, the symbol for mean is X bar. And I would just say 90 is too small, 240 is too large. This one's a little trickier. Is the standard deviation of the maximum drops closer to 40, 70, or 100 hours? Explain your answer. Okay, so standard deviation. Standard deviation says, again, how spread out the data is. Most of the data is going to be within one standard deviation of the mean. So if we're saying the mean is about that 135 value right here, if the standard deviation was 40, that'd be going out to here, to the right, and about 90 to the left over there. So yeah, most of the data is within there, but there's still a lot of data, especially over here on the left, that's outside that one standard deviation away, and generally we see more of the data within there. 70 is a little bit better. If we go from 70 to 210, that gets us to here, and this would bring us all the way down to about here. So this is a standard deviation of 70. That does get the vast majority of the data. There's still some less than it, for sure, and some more than it, but that's most of the data. Usually around 68% or 50 to 70% of the data should be within there. And that looks like a good estimate. If you look at 100 hours, 100 would go way past here and up to 230. So pretty much you would get almost everything except for those extra little outliers. One standard deviation away from the mean wouldn't normally get all of the data. That'd probably be more like 2 standard deviations away. So I would say 70 is probably the most likely here. And remember, the symbol for standard deviation is that sigma. So I'll say standard deviation is 70. And I'll explain these a little bit more than I did with the mean. It's not 40, just because most of the data would be outside of one standard deviation of the mean. And really, most data should be within one standard deviation of the mean, because the mean is the average and standard deviation is talking about the spread. And again, the reason I didn't say choose 100 is because almost all of the data is within plus or minus 100 of X bar, and that's really too much. They shouldn't have encompass all of the data, but just the majority of it. Okay. All right, so now you've got a little bit of a handle on what mean and standard deviation tell us about the spread of the data. This next one is going to rely on your calculator. So I would grab your calculator right now so you can get practice doing this. You can pause the video if you don't have it, but definitely get it out before you start this one. It says, following are the number of calories in a basic hamburger, one meat patty with no cheese, at various fast food restaurants around the country. So a bunch of different data there. It says, input these data into L1 on your graphing calculator. Use one variable stats to calculate the mean and standard deviation. And they give you some calculator instructions. Go to stat calc one variable stats for that. Okay, so if you were to count all these values, there's 32 data values. Just trust me on that one. And with your calculator, we can make the calculator do means and standard deviations and lots of other statistics that we'll need. It's a little tedious, so you got to go to stat. So stats right here, and then edit. And you should see all these lists. If you have stuff in the list right now, you want to use the up arrow to go to L1, hit clear, and then enter, and it'll clear out anything in the list. So like if I had a couple numbers in here, if I go clear, enter, gets everything out. Word of caution, don't hit delete. Delete takes away the list. You don't want that. If that does happen to you, you can insert the list again by going second delete. And if you want the name of the list to be L1 like we're used to, if you look above the 1 key, there's an L1. So you have to go second L1, enter. But assuming your list is empty, go ahead. You have to type all of these in. So this is going to take me a little while. So while I go through and type all of these in, you do it as well. Oops. So you just got to type them in and hit enter, and it should go in. And I'm going to just keep typing these in. I'm going to pause the video for a second and make it all happen so you're not waiting for me to do it. Okay, so when you get them all in, you should see L1 of 33 on that blank space. That means that would be the 33rd number to put in, but there's 32 total values, so 740 was the 32nd value. So if you haven't gotten those in yet, pause the video until you do. If you're ready to keep going, here's the next steps. So we've got all of our data stored in there now. So now I can go second mode to get out of that. And now it said go to stat calc one variable stats. So stat calc one variable stats. Now those of you with new calculators will see a whole screen come up. It should say on your screen, it should say list, and you should see L1. If it doesn't, put L1 in there by going to second one for L1. And the other thing is you want to make sure that freq list is empty. So if you've got a new calculator, you'll see freq list. You just want to make sure you leave that blank. Don't put anything in there. There is no frequency list right now. And then you can just go down and hit calculate. For those of you with old calculators like this one, it should say one variable stats. You can just hit enter. And there's a bunch of stats. So we wanted the mean and the standard deviation. Now remember, the mean is x bar. So we'll round it to the nearest tenth, I guess. So 665.3. X bar equals 665.3. And then standard deviation is this sigma of x right here, 278.963. Again, I didn't see what to round it to, so I'm just kind of picking whatever, 278.963. Now the calculator will also create a histogram for you. It says you can go to stat plot on, so let me show you those steps. So go to stat plot, which is second y equals. We want plot 1 to be on, so I'm going to hit 1, change it to on. And then in type, again, new calculator looks slightly different, but you should still see a graphic of a histogram. Go over to that and click enter. And then it'll say xlist L1, freq can just be 1, so change those if those don't say that. And then if you go to zoom 9, it'll show you a histogram. This is all the different values of these data organized into different sections of a histogram. So let's just make a basic sketch of what that looks like. So I'm not even worried about the scale or anything like that. I just want to see basically what that calculator is showing us. Something like this. And what would we say about this graph? Is it skewed? Is it roughly symmetric? It's not exactly symmetric, but it's not really skewed either because there's not a lot of outliers. So I would say it's roughly symmetric. Maybe slightly skewed, right? Maybe. Because most of the data is over here on the left, but it's roughly symmetric. All right, so that's how you input a list of data and figure out the mean and standard deviation. Now there's other statistical measures that we can also calculate with the calculator. And then if you go over to the last page, you're going to see another example. It says if you are given a frequency table rather than a list of just data, we need to slightly alter what we do in our calculations to determine the mean and standard deviation. We can still use the calculator. In example 4, it says the table below displays the number of siblings of each of the 20 students in a class. So A frequency list tells you how many times, rather than being redundant and listed all the time, it tells you how many each response was answered. So like 0 siblings with a frequency of 2 would be a 0 and a 0. And then 5 ones, 1, 2, 3, 4, 5, 7 twos, etc. We could enter all of those into L1 like that, or the calculator has a way of putting these in L1 and these in L2. So if you go back to your calculator, go back to stat again and edit. Take out all those values you put into L1. Remember, go up to L1, hit clear and enter. Put all these number of siblings into L1. So 0, 1, 2, 3, or 4. Into L2, we're going to put the corresponding frequencies, 2, 5, 7, 4, and 2. So that's what part A said to do. Enter the number of siblings into L1 and the corresponding frequencies into L2. Determine the mean and standard deviation for this group. Okay, so this time I'm still going to go to one variable stats. So calculator steps, I'm going to go stat, calc, 1 bar stats. But if you've got an old calculator, we got to tell it to consider the frequencies now. So we're going to call this L1, comma L2 before I hit enter. And I'll show you what that looks like in the calculator in a second. If you've got a new calculator, when you do stat calc 1 variable stats, you still want list to say L1, but now you do want something in freq list. You got to tell it there is a frequency list. So put L2 in frequency list. Okay, so on my old calculator here, I'm going to go stat calc 1 variable stats. I have to type L1, comma, above the 7, L2, and hit enter. Again, you can use your freq list if you have a new calculator. And then look what we got. The mean is 1.95, and the standard deviation is about 1.117. So we've got mean of 1.95 and standard deviation of 1.117. Now I said there's other different statistical measures you can find in that 1 variable stats as well. So some of these, if you scroll down, you see we've got min, Q1, median, Q3, max. There's no mode. Mode, remember what mode means? What word do you think of when you hear mode? You should think of most, the one that occurs most frequently. So looking at this list of data that we had, which one occurred most frequently? 2 siblings. So the mode is 2, not 7. 2 is the number that was responded. These values we can get from our calculator. Q1 is 1, quartile 1. And that means that quartile sounds like quarter, 25%. That means 25% of data is below that value. Maybe I should say at or below. So 25% of the data from this survey, people had 1 or fewer siblings. Median, hopefully remember that means middle, and that is on the calculator. Median here is 2. And that's also the second quartile. That means 50% of data is at or below. So half the respondents have 2 or fewer siblings, half have 2 or more. Quartile 3 was 3. And you can probably guess that's the next quarter, so 75% of data is at or below that. So 75% of the respondents have 3 or fewer siblings. The range, we always take the max minus the min. For this survey, the maximum number of siblings was 4, min was 0, so our range is 4. Interquartile range is basically what it sounds like, between the 2 quartiles, Q3 minus Q1. So in this case, 3 minus 1, interquartile range is 2. Now variance is another measure of spread. So variance is just standard deviation squared. not really used as much as standard deviation, but sometimes you might see it referred to. So in this case, it'd be, really we shouldn't round it. We should use the whole value, but for sake of argument, I'm just going to do 1.117 squared here. So 1.117 squared comes out to be about 1.2-ish. Okay. And then the last question here, how many students have a number of siblings that falls within one standard deviation of the mean? This is a question they used to like to ask on the Regents quite a bit. We've got a mean here of 1.95. So within one standard deviation means plus one standard deviation above and minus one standard deviation below. Okay, so if I wanted to figure out what value was at the mean minus one standard deviation, I would take that 1.95 and subtract one standard deviation, which is 1.117. And if I do that, 1.95 minus 1.117 gives me a lower bound of 0.883, or 833, sorry. And if I do one standard deviation above, that would be doing the mean plus one standard deviation, so 1.95 plus 1.117. Let's see what that is. Oops, I missed a 1 there. 3.067. So we want to know how many students have a number of siblings within this range. So between 0.8 and 3.07. Well, 0 isn't within that range, but 3 is. So it's all of these people are within one standard deviation away, which again is most of the data. So how many people are that? I would take 5 plus 7 plus 4. So this means 0, 1, oops, sorry, not 0, 1, 2, or 3 siblings. So we've got to take, there's 5 people with 1 sibling, plus 7 people with 2, plus 4 with 3. So there are 16 students that are within one standard deviation away. Okay, so there's your quick review of some Algebra 1 stats. Hopefully some of that looked familiar to you. Tonight's homework actually doesn't have a lot to do with that. It's some Green Book review, so make sure you do that because that will be collected and graded tomorrow. And tomorrow we'll start the new Algebra 2 statistics with a talk of the normal distribution. See you then.